Welcome back to this video series. So I will continue from our last discussion about bootstrapped sampling switch. So last time we stopped at here, step 3, that is successfully increasing the clock swing from VDD to VDD plus V in. The problem was that in the bootstrapped sampling switch, this node VP and VX nodes are high voltages, and remaining nodes VDD and ground, and maybe I should highlight within the circuit. That will be simpler to follow. Okay, so one thing I'd like to highlight is that only VP and VX nodes are above the VDD, which is the supply voltage. Other nodes are less than VDD or equal to VDD. So let me highlight VP. So you can press the number 9 button to highlight some specific nodes. And this, okay. And let me highlight different color. Okay. Oh, no, it's not good. I shouldn't use. Okay, this is good. So only VP node and VX nodes are high voltages, which is high voltage means that it is larger than VDD. Let's say V high. Suppose these nodes are higher than VDD. Other voltages, VSS, VDD, and this node is connected to VSS or Vin, so it doesn't go over VDD. So the voltages that is connected to the top plate of the capacitor that is driven by the voltage higher than VDD. So we need to take care of what are some possibilities of damaging the transistor, such that after we make the circuit and we fabricate the circuit, then the transistor may die because of the high voltages. So high voltage, it means that we have, for example, here PMOS 1 volt and NMOS 1 volt. That means this transistor can endure as high as 1 volt only. So that means VDD core, we normally call VDD core is 1 volt. So this transistor, for example, VGS, VDS, or VBS, which means body to source voltage, it should be less than or equal to 1 volt. Of course, for some safety margin, typically what foundry companies make sure is that it can at least can be safely operate slightly higher than like the supply voltage, maximum supply voltage, for example 1.1 volt. But it cannot guarantee, for example, if we drive 1.5 volt, then if this transistor makes sense to operate correctly and without damage, we cannot guarantee. So although that kind of consideration must be taken into account, and here let me run the simulation. Yeah. So if I plot it, so for example, this node, yeah, you can see that it touches as high as 2 volt. But for just to make sure if V in is driven at correct voltages, okay, it is swinging 1 volt to 0 volts. Okay, V in is set as I intended. Anyway, so this one is swinging to 2 volt, which means that the VDS drain to source voltage is as high as, let's just to 2 volt. I'm not sure this mathematical expression is correct in this case, but let's say this is correct. So if it touches as high as 2 volts, that means after we fabricate this chip, this transistor may die. Die means that is the drain to source connection may be irreversibly damaged such that source to drain voltage is connected, and then we cannot recover it, let's say. So that kind of situation is not prepared. This kind of rating depends on which process technology or process node you are using. For example, let's say 65 nanometer, the supply voltage is 1.2 volt, then definitely the maximum voltage is 1.2 volt. If you go down, in our case, this is a generic PDK 45 nanometer, we have 1 volt. If you go to like 28 nanometer, then some foundry companies has 0.8 volt, some foundry companies have 0.9 volt. And if you go down below and so on and so forth, then this one also go down. So this is a device physics. Anyway, so to protect this kind of situation, what we can choose is adding one more transistor in parallel. So in our case, this VX node is causing problem of VDS, high voltages. So if we place another transistor, then at least this middle node, this middle node will be, voltage divided from, let's say this is Vx. Let's say this on resistances are same. Then this one will be driven by approximately Vx over 2. So even if the Vx node reaches as high as 2 volts, this Vx over 2 node will be 1 volt. But that VDS of each transistor will be safe, at least. That is the core idea. And what about the other transistors here? So M8, M9, and M7. So let me figure out. There's transistors also. So if we plot P node and X node, then we have this kind of situation. And divide into different plots, or you can simply do this way. Either way is fine. So for this case, we can, probably overlay to plot will be better. So if clock is low, then VP node and VX nodes are short-circuited. VP, VX short circuit, such that VDS should be fine. VDS node should be fine. So here, you can see that VX, there are some situations that VX node and VP nodes are same here, right? There are some certain time period VP nodes, VX nodes are the same. Otherwise, those swings are, kept as high as 1 volt only. This is because other cases, then, the hold phase, that means this gate voltage goes to 0 volt, which is connected to here. And if this voltage is 0 volt, then this is also 0 volt gate voltage of PMOS. Then the P node will be connected to VDD. Then, that's all. VDS is as high as only 1 volt. So, in terms of VDS, that's fine. But the problem is that when we drive VP node and VX node, when both of them are high voltages, this is the problem of this situation. So, within this period, this is hold phase. For hold phase, there's no high voltage because we are resetting all the circuits as 0 volt, and this is a VDD, and only VX and VP nodes are high voltages. So everything else are all within 1 volt. So this is okay, but this is a hold. This is a tracking base. So during the tracking phase, we are boosting our high voltage node, VP and VX node over VDD. So this is the dangerous situation. We have to take extra care. So during this phase, okay, the VP and VX nodes are short-circuited. Okay, this is okay, but to make sure VP and VX nodes are short-circuited, this gate voltage must be 0 volt. That means VSG of PMOS circuit is higher than 1 volt, which means VDD. But this is a dangerous situation. So let me also take an extra look of this PMOS transistor. So for this PMOS transistor, the drain voltage is VDD, as always VDD. So no matter how VX node is boosted over VDD, its difference is always within VDD. So let's say this is a 2 times VDD, but still the difference is VDD, and this is also, let's say, 2 times VDD, still VDS is within VDD. So there is no serious or dangerous situation happening at this PMOS transistor. So we need to make sure VSG of on PM1 transistor is staying within a proper voltage, which is 1 volt, within 1 volt. So for that purpose, we need M8, M7. Let me highlight M8 and M7 and M9 transistors are required, as I explained during the lecture. And also you can find Professor Rajabi's magazine paper about the more detailed explanation. So this is a step 4 circuit. We have stacked transistors, M3 here, and we have some protection circuits. This inverter-like circuit, PMOS and NMOS, and another NMOS is here. The basic operation are already explained during the lecture, so I will not provide too much details about the circuit operation. So verify the bootstrapping operation. Does yes, okay. So because I already have learned the simulation, including step 1, 2, 3, 4. So VX, let me check VX first. Then close it and open it again. VX node, yeah, this is boosting correctly. Vin plus VDD. Vin plus VDD node is, let me see, maybe should be better to plot this way. Vin plus VDD during the track base. Yes. So basically X4 node is same as this node. I just assigned X4 node to the output setup. So anyway, it reaches quite nicely as high as Vin plus VDD. Of course, it cannot perfectly exactly touching Vin plus VDD node, but still, yeah, this is quite nicely touching as high as Vin plus VDD. If you really want to make sure, okay, I want to make the gaps even closer to Vin plus VDD, you can then definitely increase this, for example, bootstrapping switch cap to 1 picofarad. But there is always a trade-off. If you increase that, then those power consumption of this bootstrapping circuit will increase, and also input capacitance of preceding buffer stage. For example, we have buffer here that is driving the input pin. Then this one is somehow connected to bootstrapping capacitor, that means it is equivalently during the tracking phase. It is equivalently the same situation to the circuit that has a buffer has an output capacitor that is added as a C equal to, let's say, 1 picofarad. So that means our GM over C will go down. That GM over C means the gain bandwidth of this buffer circuit. Then our speed is reduced. So there is some trade-off. All right, and check that no transistor node voltage exceeds approximately VDD in terms of VDS or VGS. You may provide individual transistor terminal voltages to verify. Yeah, so as we verified our design, the schematic and some verification steps in our own way. So this is a VX node, and for VDS voltage verification, you can simply look at this intermediate node. You can see that it doesn't touch as high as 1 volt. It goes slightly touching as high as 0.9 volt only. So that means VDS is literally less than 1 volt, and this VDS is also less than 1 volt because this is also touching as high as 2 volt only. So this is done, and other cases, for example, source to gate voltage. This is also driven as a 1 volt only, which is good. And of course, there are some peaking situation. Let me delete the other nodes. There are some peaking situations such that, okay, like this node touches, like, yeah, it's still higher than 1 volt. And this is also going down to 0 volt. Okay, this is some sort of situation you face. And then you may ask, oh yeah, this is not a good situation. This is problematic. As I mentioned, this is okay in practice because the foundry companies make sure this kind of transistor can endure slightly higher than VDD. That is one. And second matter is that if we add a capacitor, let's say very small capacitor, no depth of ferrite, and let's see what happens. Okay, and if I run the simulation again, and if we plot VSG, then you can see that there is some sort of reduced peaking here. This is we call as a decoupling capacitance effect. And this one doesn't look like it is reducing that much. But if we increase the capacitance, then I believe it will be more stabilized. So what I want to say is that this is similar situation as we studied in continuous time filter. It looks like it is stabilized with some sort of less phase margin, right? Because of this oscillation, response. Then if we increase the capacitance, then its oscillation like a response, the frequency is reduced, here, from here to here, the speed is reduced. That means if we add more capacitance, then is kind of small system. Within the small system, its Bayesian margin will increase. That will slow like this. Then the question is that, do we need to add this kind of capacitances? In practice, no, because after we fabricate the chip, then there will be some plastic caps will be added in rear layout, after doing layout. So, yeah, by that effect, those individual nodes will be stabilized one step further. So combining all together, it will be okay if we, even if there is some small peaking situation. Of course, if this peaking is too high, as high as, for example, like this, then it will make some problems, I believe. But in practice, this kind of small peaking is okay. So anyway, so what I want to say is that it's just as ignoring this part of peaking, this voltage and this voltage. You know, these steady state voltages are within 1 volt. All right, and compare the output waveform with the circuit in step 3. We can compare 3 and 4. And if I also plot in and in plus VDD, and you can see that this is input, and this is input plus VDD, and this is X node of step 3 circuit here, step 3 circuit, and this is X node of step 4 circuit. So you can see that there is a slight decrease of bootstrapped, the bootstrapped circuit, bootstrapped voltage. Probably this is because of some more added circuit components here. Yeah, let me see what is happening. Yeah. So there is, you can see that at the VX node, we added one more transistor here. That means added plastic cap. And as we studied in previous quiz and lecture slide, if there is more plastic caps, then after charge sharing or after charge conservation law, after applying charge conservation law, then the bootstrapped voltage will be decreasing because of that plastic cap. Okay, then let me move over. So in step 3 and step 4, the bootstrapped capacitor CP determines how well node X can be boosted after the supply voltage VDD. So we already discussed about this trade-off. If bootstrapping's capacitor, this one is too high, then we are reducing the bandwidth of the preceding buffer stage, which is good, which is not good. If we reduce the capacitance too low, then the bootstrapped voltage cannot be touching as high as we expect. So bootstrapping error must satisfy within the 10 millivolt. So we can verify this. Let me see. And I set as a 100 femtofarad in this case. So for example, X4 and B plus VDD, we can do like in this case, press select this B plus VDD and then press Control and click X4 and go to calculator. Okay, so we already selected both of waveforms. We can just simply click this minus button. Then you can see this is already calculated well and plotted. Then let me see, Vin plus VDD, wait. U-bolt. Yeah, okay. Here and here. Here and here. Then you can see that during the track phase, this voltage is indicating the amount of error during the track phase. This voltage is indicating the amount of error. And Vin plus VDD is always calculated without, no matter how our circuit is operating, it's reset phase or tracking phase, hold phase, tracking phase, no matter how our circuit is operating, it is just simply Vin plus VDD. So X4 is resetted, even that phase, there is some error. So you can simply watch this node voltage, or there is one method, or another method is that bootstrapped voltage. Then you can simply click this node and click this node, which is capacitance voltage. Then you can see that the lowest bound of this bootstrapping action can be seen. So when the voltage is touching exactly as high as 1 volt, that means we are resetting this bootstrapping cap. And during the bootstrapping action, which means tracking phase. So this is hold phase. This one is a tracking phase. This one is a tracking phase. And then we can see that this tracking phase voltage is not touching as high as 1 volt. So we want to make sure at the worst case scenario, it can be still touching within 10 millivolt boundary. Then what is the minimum capacitance to achieve this? That is the question. So if we increase the bootstrapping cap, then you can see that. Or let me see, I save it as an output here. Oh yeah, I already saved it. So here, I already saved it. If I append this, let's make sure, okay, both voltage nodes are same. So I can simply check this PT4. And in this case, I can calculate the minimum voltage here and save it as an output. Okay, then, yeah, so can run some parametric sweep. Let's say cboot and femto to put about 1 pico and 10 steps. Okay, then it sweeps from 100 femto to 1 pico by 100 femtofarad step. If we run it, other things, plot of Vx and V plus VDD. Yeah, we can also do this part. And what is the minimum value of, what is minimum value of CB that satisfies this, the specification? We will find it. Why does too small capacitor reduce the bootstrapping level at node X? This is already discussed, so I will not discuss too much about it. Okay, so you can see that to make sure this error is within 10 millivolt, then it should be as high as 990 millivolt. Yeah, we can see that it is easily measured with 993 millivolt at 200 femtofarad. So yeah, if we assign 200 femtofarad, you can achieve this. And for verification, maybe we can also run 10 cycles of input frequency, as one of our students asked during the lecture. And Vx 4 and Vin plus VDD. And let's run it. So there are multiple cycles of X4 and Vin plus VDD. You can see that it is nicely operating with our expectation. And at the worst case, because we are calculating the minimum voltage of bootstrapping cap, we can see that it is still within 10 millivolt boundary, error boundary. All right, and the next question is validation with comparison with baseline switch. So let me see. So for this case, like move out. So input is sine wave input frequency with 100 kilohertz. 100 kilohertz, okay, amplitude 500 millivolts. Okay, I think this is already done, right? So input is here. Yeah, 500 millivolt bias and amplitude is 500 millivolt. In this case, amplitude means that really amplitude here. It doesn't mean peak-to-peak voltage. This is amplitude. This is amplitude peak-to-peak. Peak-to-peak. And the supply voltage is 1 volt and capacitance 10 femtofarad. I think we already saw it. 10 femtofarad here, 10, 10, 10, 10. And at least 2 to 3 input cycles. Perform the transient simulation for both circuits. Baseline MOS switch we have here. We have here baseline and full bootstrapped circuit here, and include side-by-side screenshots. So you can do that way. So input is here, okay, and output 0 here, output 4 here. And for clarification, maybe we can also think about including clock. And let's divide it, and this is already same. And can maybe consider merging it this way. So you can see that for bootstrapping switch, it follows very nicely. No matter input is high, input is low, it follows the input voltage during the tracking phase, which means when clock is high. Yeah, even during input is high voltage, yeah, if the clock is high, it follows very well. But for output 0, because of the on resistance, it cannot follow that much well. And tracking actuals near supplied rails, we have already done it. Sorry about this. This is repeating again and again the same question. So apologies. And any visible distortion, there is a distortion here, and MOS only, and held voltage levels more accurate in bootstrap case, yes. And PSS plus PAC. So this is verification about the bandwidth and the PAC. So we can run, for example, simulation setup. DC bias is 0, half VDD and VDD, and input AC volt is VC equal to 1. And we check PAC is okay. Set it nicely. Clock is 1 megahertz, 1 megahertz. And yeah, okay, so we can run the PAC simulation. Currently, VDC is half VDD. And then PAC setup is, let me double check PSS setup. So, okay, so for running PSS simulation, we need to turn off this frequency setting. Because as we discussed, PSS doesn't converge. There is 2 different frequencies. which cannot be divided each other. So what I mean divided each other means that if we set input frequency, in this case 10 kilohertz, actually this is okay to run for 100 kilohertz, and this is a 1 megahertz, but PSS runs based on this lowest frequency. So we want to run PSS based on clock frequency. So we should not set lower than the clock frequency if we want to run the steady state condition based on clock frequency. So that's the action why I removed frequency part. And so harmonics 10, you can also increase to 20, that's fine. But for this case, I will just keep going on 10. And we are looking at clock frequency over 10, 10 times clock frequency here. And the number of points, yeah, I will just stay with this. Oh, sorry. I'll just stay with logarithmic 30 points. Of course, this is recommended with 1,000 points for very accurate accuracy of our simulation results, but for simulation time and for the duration of this video, I will just run with 30 points only. And maximal side events, I set it as 0. So baseline MOS and bootstrapped sampler. Okay, then yeah, so we can run this. Let's see how it goes. Okay, it's complete. And PAC gain dB20, right? So dB20 here, PAC, okay, and if I plot it, you can see that it shows our expected result of this the track and hold operation, which is a theoretical analysis that we did. This is alpha 4. You can see that our bootstrap switch is having slightly higher response at high frequencies. So what I want to say is that when our DC voltage, sorry, not this one. So our DC bias of input voltage is VDD over 2. VDD over 2. This is still okay, right? To sample our voltage correctly, because I set it as VDD 0.5 volt. But let's see what happens if I increase this one to 1 volt. So this means that now we are changing not VDD over 2, we are setting DC offset as a VDD here. VDD. Then what will happen? Let's run it. Okay, and then if I refresh it by pressing Ctrl R, then you can see that for output 0, it does not work at all. It has really like minus 40 dB and going down like this. This is because of, it cannot track well the input voltage. So this is, that is the reason. And for the bootstrap switch, it's still within our expectation as we have seen. And video voltage, the steady state, which where it is settling for is minus 6 dB, which means 1/2. Half value, as we verified in theoretical analysis in equation. And I will just skip for Vin equals to 0 volt, which is obviously you can check it. It will show very nice smooth PAC curve for both of baseline MOS and bootstrap switch. Okay, and here we verified we input DC is VDD, should maintain near unity gain. Near unity gain. Yeah, so here it shows DC gain is very close to unity gain. Here only minus 7 millidB. That is the intention. And I think there is some mistake here. It should be like near unity DC gain. And explain why the bootstrapping action preserves VGS equal to VDD even when V equal to VDD. This is already we discussed. Sorry about it. It is asking the same question repeatedly over and over. And discuss possible causes if you any gain degradation in the bootstrapped case, and you can discuss. So if you experience, for example, this one DC gain reduction, like this, then this is not a good situation. So in this case, if you set, for example, here, like if you set like this switches length is too high, for example, then it will not be good enough to correctly follow the input and output. This is my assumption, but I'm not sure. Let me check it. Make editable, and if I set the length as let's say 10 micron, it's a very extreme case. Let's see what happens. Our VDC is 1 volt and VDD is 1 volt. And we don't want to check, obviously, the baseline switch case. If I refresh it, then, yeah, interestingly, it is even increased to higher than 1. Which is not expected. So honestly, I'm not sure. I have not verified this action, but we can verify this for the transient simulation. Oh, this is too long. We are simulating for 10 cycles. It's not necessary. Go back to 2 cycle and let's see. So this is input voltage, and this is oh no, we are not adding the AC signal. Put in, and let's see, this one is back to 0.5 volt, such that input voltage swing is this. This is 1 volt, this is 0 volt. Okay, if I refresh it, then yeah, this is 1 volt to 0 volt swing. And if I plot alpha 4, then let's see what happens. Yeah, looks like something is happening here, right? So it even touches to like negative volt, right? So what is happening here? And then when the tracking phase is completed during the hold phase, it goes back to like what is it, 0.5 volt, slightly higher than 0.5 volt, and it also touches. So it looks like here, this is tracking, and then after finishing the tracking, it moves down like this, which is weird, right? Tracking moves down, tracking moves down. So this is the phenomenon we normally call clock beat through. So because we increased length to 10 micron. So this transistor's size itself, width, and this is the length. Let's say this is the length, and this is the width. Then this transistor size. Oh, it doesn't look like our case. Okay, so this is the length, and this is the width. Because we only increase the length very, very long, 10 micron. Anyway, so plastic cap gate to source plastic cap will be increased in this case. I mean, it is already increased, sorry. So during the bootstrapping action, this one boosted to VDD plus Vin, and then it is reset to 0 volt. So there is some sort of negative swing. And if there is some, I am zooming in here. If there is some negative swing here, this is a negative swing, then we have cap, and there is another cap. So there is a voltage division here and here. So this voltage is instantaneously affected by the negative swing action. So we call this kind of phenomenon as the clock feed through. So you can study about this phenomenon by reading Professor Rajabi's textbook, although we have not managed to discuss about this phenomenon during our lecture. This is what is happening. So we should not increase this plastic cap too much for designing the transistor, each transistor. So let me make it back to 45 nanometer. Yeah, so because of this action, probably, this peak-to-peak voltage here, it is increased from here to here. But I believe this kind of phenomenon is included as a gain increase, but it's not our, intention. It is not as we designed to be like that, which is not good. So this is a discussion part, and this input range comparison, this PAC gain, so sweep VDC from 0 volt to 1 volt. And this is the last section. So we can run similarly. Let me move back to our PAC setup. So we want to make sure this is disabled, and as just simple verification, let me run it once before we do the parametric sweep. Okay, so PAC gain. So we are specifically discussing and exploring about DC gain or PAC. Okay, so voltage PAC dB, this one here as we observed, and this is our bootstrapped switches PAC. So for this one, for getting the DC part, you can clip it. So for example, this is 10K. Maybe we can average for 10K to 11K. Let's say 10K to 11K. Plot it, then you get it, right? This small range, and then average. Okay, then you get 3.9 millidB. So 3.9 millidB, right? So this is a number, so we should not save this number. So we should save the expression, not the number. So In this case, you can simply double click this one, then it go back to like this, and then press this. So this is our expression, PAC BC baseline. And for others, conditions are the same. We can simply put output 4 as I assigned here. Then save it to the output. In this case, this one is PAC BC gain is bootstrapped. Okay, clear. And we can run the parametric sweep. So VDC 0 volt. I think this is so obvious, right? I mean, for even at what I want to say is that even at 0.5 volt, its DC gain is quite similar each other. So we don't need to actually run for the full sweep range. Of course, the question is asking 0 volt to 1 volt, but for this video, I will skip it. So I will just run 0.6 volts to 1 volt and total sweeps from 0.6 to 1 volt. If I sweep 5 steps, then yeah, it will show this way. Or if I increase by, let's say, twice, then it will sort out like this kind of setup. Let's see. Oh, what physical mechanism in the bootstrap circuit enables this wider range? Sorry about that. This is asking the same question again and again. So we discussed because VGS is made sure as approximated to VDD no matter Vin value it is for the bootstrap switch. Are there any remaining limitations of the bootstrapping topology we already discussed in previous section? Sorry about it. In previous section that if the bootstrapping cap is too high, then it reduces the preceding buffer stages bandwidth, and DC input range we will check. Okay, so for the baseline case, bootstrapping case, we can see the difference. And if I plot as we learned from our smart student, user window, okay, then we can plot it. And for case, we can also plot it. All right. So, let me see. It looks a bit. Oh yeah, so this is a milli-dB scale. So you can see this is a milli-dB scale. It is not a dB scale, it's a milli-dB scale. So even at 1 volt, its gain decrease is as low as only 7 milli-dB, which means minus 0.007 dB. This is, of course, this is much, much better then minus 3 dB. So this is clear. Good. All right. And what about the baseline switch case? So you can see that until like 0.73 volt, it can ensure minus 300 millidB, which is still less than minus 1 dB, but it goes to, it is lagging. Okay, it goes to minus 13 dB suddenly at 0.8 volt. So if I zoom in, then, oh no, sorry, this is already touching at minus 3 dB here. So here we are already touching less than minus 3 dB. This one, right? So we may conclude that our baseline MOS switch cannot ensure higher than approximately 0.777 volt. Of course, if we, this is just some 3 dB criteria, 3 dB based criteria. If we want like high resolution ADC or high speed ADC, then definitely this is not good enough. Minus 3 dB is not good enough. So this is our conclusion for the Bootstrap switch. It can make use of every single voltages of DC bias voltage, no matter this is 0 volts, 1 volt, every single region is usable for bootstrapped sampling switch. So we verified this way. Okay, this is a conclusion. So thank you for watching this video, and I will try to cover the next CAD exercise, the next video.